Hello, everyone, and welcome back to Teach Astronomy. My name is Victoria, but you can call me Vicky. And I'm here with our special guest today, Judah. So Judah is a UCLA student studying astronomy and physics, similar to another guest that we've had on the channel before. And I brought him here to talk about his research, and you guys can ask him questions, and we're just going to hang out and have a good time. Be nerds. So, Judah, I gave a little intro, but would you like to kind of explain, introduce yourself, give a little quick summary of you?
Yeah, totally. So, first off, I want to say thanks for having me on, Vicky.
Thanks for
Very
being
much an
here.
honor. It's my first podcast, actually. So, I'm nervous. Um, let's see. So, I am a grad student at UCLA, third year. So, I guess you guys probably know Aiden pretty well at this point. So, yeah, I'm in Aiden's year. We both study exoplanets. Um, let's see. So I'm from California originally, the Bay Area, if anyone knows, like Marin County, just north of San Francisco. And I went out to Indiana, so University of Notre Dame, to study physics and math for undergrad. And then right around the end of my undergrad, I started to get like to look around for what I actually wanted to do after that. And so like the physics that I had done up to that point to me was a little, I don't know, it just didn't have like the right combination of sort of the experimental side and also the theoretical side. I had done a couple of things that were like heavily experimental and then some stuff that was more heavily theoretical. And so I said, well, astronomy, like various areas of astronomy seem to have like really good balances between, observing and then some instrumentation and also some theoretical stuff. So I was like, okay, I'll kind of make a bit of a switch. It wasn't a huge leap to go from physics to astronomy, but yeah, we didn't have an astronomy program at Notre Dame, so it was a little bit of a leap. And yeah, I was fortunate to get into UCLA and came out here and have been studying exoplanets and astronomy ever since. So
Nice.
yeah, good time.
That's awesome. So, I have some questions for you guys, but for you, but but chat. If you guys want to put your questions out for Judah, feel free, and I will field those for you guys. But to start, I guess, so you talked a little bit about how in your undergrad you focused on physics and math, and then you found your interest in astronomy. Where did that and you said a little bit about like the instrumentation mix and everything like that. How did you how did you decide that not only astronomy was something you were interested in, but like when you're looking at different graduate schools, sorry, when you're looking at different grad schools and seeing the different research that people do, you see UCLA, and with grad programs, you usually want to be like, okay, and this person might be able to be my advisor, and I'd like to do this kind of research. Like, how did that come about? Like, how did you find your interest in what you do now?
Yeah, totally. So I guess first part of that is kind of how I switched from like physics to astronomy. And I mean, in a way, it's a tough question, but I also kind of like having this because I feel like there is a popular picture, especially among the sciences, where everybody has their calling, and they just know that something is what they want to do, or it just comes to them, like a message from God, and now they know I need to study this thing, and it's what I'm meant to do. And for me, it wasn't really like that. I was kind of, like I said, just doing working in various labs as an undergrad, and I found like useful skills in different ones, and it was fun to just kind of do research and to get a taste of that. But I felt a little bit aimless, like I wasn't really interested in anything. And then I was basically just thinking to myself, like, this is like the summer before my senior year, or like the spring of my junior year, whatever. And I was kind of just saying, okay, well, I don't really picture myself doing any of the stuff that I am currently doing or that I have done in graduate school. So what is something that I would want to do where like something that I picture it in my head and I say, that's so interesting that I could picture myself like doing that, for years at least, if not for an entire career. And so I kind of just paged through stuff in my head. I was like, all right, so various types of astronomy. I was like, black holes are cool, cosmology sounds interesting. And then on the physics side, I don't know, particle theory or something like that. And all of them, they had their pros, and it wasn't super obvious. And I was kind of back and forth on different ones. And then I got to exoplanets, and it was a little bit of a snap decision, but it's not like I was super self-assured. I was kind of like, exoplanets sounds so cool. I could definitely see myself doing that, but I really have no idea, about all of the details. And, since then, I obviously have learned more of them, and I have found that I think I was right in my guess. But I just wouldn't want anybody to, be thinking about making a change, like especially if you're a high schooler or an undergrad, and think like I need to be divinely inspired, about the work that I want to do.
Yeah.
Because I think, at least for me, I wouldn't speak for everybody, but I think that is not, that's something that you see in the movies, but it doesn't have to be the case at all. So for me, I just kind of said, what would I find interesting? What when I hear it sounds like so cool that it would be like mind blowing to work in that field. And for me, that was like searching for extrasolar planets. And so that's how I chose that. As far as UCLA, it was, in a way, a similar situation to what I just described, because a lot of people, again, have the same thought process where they say, I've dreamt about going to such and such school since I was a little kid. And, it's where my parents went or something like that. And so I'm definitely going to go there, and it'll be the end of the world if I don't. And again, that can like ruin a lot of people's ambition if it doesn't happen, which is so often the case. You see movies about someone getting into Harvard because that's where they always wanted to go. But of course, the vast majority of people who apply do not get in. And so,
exactly.
So for both undergrad and graduate school, I didn't get into like my top choice, but in both cases, my top choice was kind of ill-informed. Like I didn't, I had picked my top school based on what I had seen in the movies, right? Like, it's kind of weird to have a high schooler be like, where do you most want to go to learn about stuff? And I don't know, as if you really know much.
As if we've ever made that decision before. Like,
exactly. At least I hadn't. I don't want to disparage other high schoolers' abilities to choose colleges. Mine was not especially astute. But anyway, so it was kind of valuable in both cases, where I got into UCLA and I was like, oh wow, fantastic! I'm glad to have gotten in anywhere, but I'm waiting on these other places that I really want to go, just because they were like name brand, and I was like, oh, it must be so good to go there. And then UCLA ended up being like the best place that I got into, and I was like, oh, and also side note, my girlfriend also goes to UCLA. She studies biomedical engineering, so she's in a PhD program as well, but a little bit removed from astronomy. But that was great. So that was really like the big sign that we were both going to go here, is that we both got in, which looking back, I didn't realize, I think, how lucky that was.
Yeah.
We both got into the same. Yeah.
Very lucky. Yeah.
And it wasn't, we both got into basically like two places. So I got into Notre Dame, and where I was an undergrad, and UCLA. And so it wasn't like we both got into like 5 or 10 places and one happened to overlap. Like we both got into like 2, and UCLA overlapped. So that was awesome.
Yeah.
And then at the time, again, like just like when I had gotten into undergrad and I didn't realize how lucky I was to go where I went, I got into UCLA and I was like, yeah, I guess, I'll go here. I mean, it's where I got in. And now I'm like, wow, this is, pretty much as good of a place as I could have wanted to go. So then, and of course, pretty much any place is like what you make of it. So I found that, the opportunities are definitely there.
Yeah.
They're definitely here, and they're wherever any person who's listening is at, they're absolutely there. If you're willing to go out and get them. That's just sounding like a Disney inspirational speech.
I was just at Disney yesterday. It's very, very inspirational.
Perfect.
But yeah, that's it's very much like a similar. I had a similar situation when I was looking for undergrad, because I was like, I went to school for film and television. I think you knew that, but I've told the chat once or twice. And I originally applied though to like a bunch of different schools. Ended up going to the University of Arizona, but my top school was like Northwestern. For whatever reason, someone once told me that Northwestern was a good school, and I was like, I'm gonna get into it. I didn't.
Yeah.
And I'm so glad I didn't, because I don't think they even have like a creative film program. A lot of places have like a broadcast program, but which is very different from what I wanted to do. But it's that idea of like, yeah, you're told that these big prestigious names are going to be the only way that you're going to like have the best education, but like you can go anywhere and like find a place that fits you really well. So that's very cool. So, getting a little bit into the actual research that you do now that you're a grad student at UCLA. So, you do some exoplanet detection and research work using the radial velocity method, which for everyone else, it's different from what Aiden's talked about, what he does. Also looks for exoplanets, but using a different method. So, do you want to first talk about what the radial velocity method is and how you use it to find extrasolar planets?
Yeah, definitely. I don't think I have a good diagram or anything up, so hopefully we can venture into imagination land.
I might be able to find one also.
Yeah. Oh, yeah, that's true.
Yeah.
So, yeah, the basic idea is that when we think about planets that are orbiting a star, at least, that my first impression was, okay, the star is sitting at the center, planets are orbiting around it, and the star is basically just stationary. It's not moving, it's kind of sitting right in a well-known fixed location. As it turns out, that is a good approximation in most cases, but it's actually slightly wrong. And it's very important that that's slightly wrong, because it's what helps us to detect these planets. But the way that it's wrong is that rather than planets orbiting a stationary star, what's really happening is that the star and the planet are both kind of orbiting the center of mass of the system, which is some point that's very close to the star, but is not quite at the center. And so what this means from our perspective is that, yes, the planet is going around in this big orbit. For example, the Earth takes a year to go around the sun, but the sun is also tracing out a very teeny tiny circle basically around a point that's a little bit off from its center. So it's almost just like wiggling back and forth, so it's not really even tracing out a full circle. It's kind of just wobbling back and forth. And this is really, sorry.
Oh no, I was just gonna, I found a GIF that I accidentally put over our faces for a second, but I was gonna show chat, and it's a pretty solid depiction of what you were just explaining, so they can get a visual on it. So you guys can see, this would be the star, this is the planet, and the orbit. Like they're both orbiting the center of mass that is kind of an invisible point next to the star. And there's a chart next to it that shows spectra changes and stuff as well. But yeah, but exactly. You were saying.
Right. And so then, although the star is moving basically in two dimensions, it's like tracing out this circle, what we, using the radial velocity method, what we can trace or what we can observe is basically just its back and forth motion. And so that's why it's called the radial velocity technique. It's because the motion that we're sensitive to is the motion along the radial direction. So when you talk about the radial direction, it just means, toward you or away from you along a radius. And as you can probably see, I can't actually see the GIF, but probably what you're seeing is that the spectrum of the star is moving back and forth between red and blue. And is that right?
Yeah. It's
cool.
They've got like the speed chart of it, like basically, either when it's moving towards us and then moving away, and the spectra is shifting.
Exactly. And so for anyone who's not familiar with just the idea of Doppler shifting, the analogy that I really like is of an ambulance that's like moving toward you and then moving away. You can hear that when you're standing still and an ambulance is coming toward you, it kind of sounds really like high pitched by comparison. And then as it leaves, it comes to a much lower pitch. And so the idea is that any source that's emitting waves that's moving with respect to an observer, as it approaches the observer, those wave fronts tend to pile up, and that results in basically a higher frequency of whatever wave is being emitted as perceived by the observer. And so for an ambulance, that wave is a sound wave. And so what you perceive is a high pitch in your ear. And then as it leaves, you're perceiving a lower pitch because those waves are elongated. Elongated as the ambulance moves away from you. In the case of light, light is also a wave, but the way that you perceive changes in the pitch or the frequency of the light is as a change in color. And so, although it's completely imperceptible to a human eye, what's happening when the star approaches Earth for just a brief while, it's just moving towards us for a few months and then away from us for a few months, for example. But as it moves toward us, that light looks a little bit more blue than it would normally. And then as it leaves, it looks a little more red. And so if you can pay attention with really precise instruments, you'll just see that the light that you're looking at looks red, then blue, then red, then blue. And the rate at which it changes back and forth can tell you about the period of the planet and therefore how far away it is. And then how much it changes, if it goes really red and then really blue, then that tells you something about how big the planet is. So it's actually like a very rich technique. Like you can get a lot of planetary parameters out of what is essentially just looking at colors changing back and forth. But that's the basis of it, and it's what I do. So it's cool.
Yeah, it's really interesting because I feel like radial velocity is less talked about as far as when in a lot of outreach stuff. I feel like the Doppler method is usually, or not the. This is the Doppler method. What am I talking? Or the transit method is the thing that's like usually talked about. With the whole and you can see it pass in front of the star, and if you see it several times, then you know that there's something that's actually like orbiting the star. But the radial velocity method is also super super interesting. And like you said, it gives a lot of information about like what this planet could be that's orbiting the star. So with the radial velocity method, is there and I know this is specifically what you research is some giant planets, giant exoplanets. But is there a limit to I guess a lower limit to how big a planet can be in order to be detected by this kind of method?
Yeah. So just like with any method, you run into kind of instrumental precision errors, or I should just say precision errors in general. They aren't necessarily from the instrument that you're using. So for example, for the transit method, you're going to have kind of a minimum planet radius that you can detect. Otherwise, the dip in the star's brightness is not really big enough to be picked up. And in the case of the RV technique, it's a similar issue where if a planet is too small or too far away, so it happens that as you get farther away, the star also moves more slowly. And so that creates a smaller signal. So if a planet is too small or too far away, or some combination of those two, then the changes in radial velocity that it induces in the star are too small to be picked up. So this, a very notable lower bound is the Earth, essentially. So a planet of the Earth's mass and at the Earth's separation from the sun, which is, one astronomical unit, or that corresponds to a period of exactly 1 year. That causes a change in the motion of the sun that we would not expect to be able to detect if there were an Earth-like planet somewhere else. So that's kind of a limitation that we're definitely looking to probe, or to expand on, because if we want to find planets that look like the Earth, both in their composition and in their orbital parameters, then we need to be able to get down to that level. One of the really tricky things, though, is that you can be limited by the precision of your instrument. Just an example, I guess, would be like if your telescope is not focused correctly, and so you're seeing like fuzzy images, that's something hopefully that, professional astronomers have sorted out, but
Yeah.
that would, just to give you an example. So your instrument can be precision limited. But one of the tricky things about the radial velocity technique in particular is the limitations imposed by the star itself. So when you're thinking about the RV technique, you're looking at a star. And for reference, the radial velocity that the Earth causes in the sun is on the order of like 10 centimeters per second. So that's a velocity that you can actually think of, in real life. Like, I don't know, if you have your hand here, 10 centimeters away,
Yeah.
like this is how much like the sun, like it's moving at like that rate
Per
due
second.
to the Earth.
Yeah.
Yeah, 10 centimeters per second.
And that's just due to the Earth, not like Jupiter and Saturn, which is, I'm sure, a whole other issue is having multiple planets in a system. But
yeah, exactly. Yeah, but so if the Earth were the only planet in the solar system, and if the sun were, a perfect sphere that didn't change at all due to like, the explosions that are going on inside of it, then at any given time, as the Earth orbits the sun, if you were to just look, if you were somehow stationary and you were just looking at the sun's motion, it would just be moving like that. And then, of course, over the course of a year, it would eventually like, turn around and start moving the other way.
Yeah.
But 10 centimeters per second, it's like oddly small.
Yeah.
It's nothing like speed of light or something. No, 10 centimeters per second. And so you can imagine that, yeah, you could detect that if you had just this solid ball, like a nice chrome sun, just like a perfect sphere where you could easily tell where the surface of it is and it's moving back and forth. But of course, the sun is like this giant burning ball of gas with huge explosions going on all over the place, and it's got like solar flares, and there are big plumes of hot gas that are like bubbling up to the surface, and then cooler plumes that are like falling down. And so there's a huge amount of noise that's associated with the surface of a star in your radial velocity data. So basically, you're looking at the surface of this thing, and different parts of it are moving toward you, like those plumes of hot gas that are rising up. They're actually moving faster toward you than the rest of the star. So those look a little bit more, we say, blue shifted. Yeah. So just like when the whole star moves toward you, the whole stellar spectrum is blue shifted. And certain parts of the star can be even more blue shifted than others. And likewise, if some gas is cool and it falls back in closer to the core of the sun, then those parts are red shifted. And so the problem is the surface of your star does not look uniform. There's a certain amount of, static basically that you're looking at. And it turns out that a lot of stars have this static that creates an error on the order of like a meter per second. So like 10 times the amount of change that the Earth is causing can be caused just by the error of the star. And so that's that's like an immediate problem to being able to find anything that's smaller, that's smaller than like 10 times the size of the Earth. Mm-hmm. And so this is one of the challenges that faces RVs. Basically, we're looking for more precise instruments and then complex statistical techniques to try to overcome this noise floor imposed by the star. So very long-winded answer. Yes, there is a lower limit to the types of planets that you can find. And for reference, the Earth even is something that's kind of like, the gold standard that we're searching for is being able to get down to about 10 times what we can get to right now, which is like a meter per second roughly. Yeah.
That's very cool. And one of our viewers, Slight Quills, actually asked a question similar to what I was about to ask. So they said a wobble would only tell us the weight on the other end of this, star versus exoplanet scale, right? So it's possible that some of these large planets we're finding might be the weight of several planets on the other end of the scale. And I was going to ask you about how you deal with the possibility that there are multiple large planets in a system, and like if there's a way to differentiate that, or how that affects the star and its movement.
Yeah, definitely. So if you're looking at that GIF still, I don't know if it's still up.
I can pull it up again if you. Let's see.
Yeah, or people probably remember that basically a single planet is tracing out a nice, a nice wave. It's probably on a circular orbit, and so that would be a sinusoidal wave. Basically, just what you think of when you think of, something creates like a wave signal. It just looks like it goes up and it goes down, and it's got this nice curve to it. Of course, if the planet is more eccentric, so if it has like a really oval shaped orbit, then that curve will look a little bit wonky, like it might go, gradually up and then come down really fast. So there are, some peculiarities to the shapes of those curves. But basically, you have this one nice curve because there's only one planet. In the event of there being, let's say, two planets, then it's actually a really nice, relatively nice outcome that's produced in the radial velocity signature that we observe in the star. And what happens is just that those two signals that are produced by these two planets, let's say one of them is really short period. So this thing's going around in maybe like a couple of hours, which are some of the really short period planets can have periods. What takes us a year to go around the sun on the Earth might take, 15 hours or something for a planet.
It's moving fast.
Yeah, it's booking it down there. And so what you're going to see if you look at the RV, what's called the time series of this star. So the time series basically just means that you went to a certain time, you plotted the radial velocity of the star, you move over to you wait a little bit of time, you plot the new RV. And so what you do is you trace out this curve, which is exactly what you're seeing in that GIF. Mm-hmm. So if you look at the time series due to just the inner planet, you'll see this really high frequency change, right? So let's say you looked at it for a month. Well, then it completed a full orbit in like half a day. So you should see like 60 full orbits over the course of the month. So bzzz. Now, on the other hand, if there's another planet out here that has an orbit of, let's say, 1 month, then in that same month, it'll have completed one orbit. So it looks like that. And both of those signatures should be imprinted on the signal that you're seeing. And what you'll end up seeing is the big curve with all of these little wiggles imprinted on it.
Oh, yeah. Okay. That's very cool.
Yeah. And so as it turns out, like this was one of the first things that I thought of when I first got introduced to the RV technique. So it's definitely something that, we need to disentangle. But it's basically all you have to do is kind of separate these sine curves that have been added together, or these periodic signals that have been added together. And once you do that, you can identify each planet individually. And sometimes the data is clean enough that you can just do that kind of by eye. So there are some data sets where you can actually look at them and you see a little wiggle that's kind of imposed on top of a long wiggle. And you're like, oh, cool. Short period, small planet, overplotted on a long period big planet. Mm-hmm. And those are the ones that are easier to see. So yeah, that's a great question.
That's really cool. It's very interesting. Thank you, Slate Quills, for that. So going a little bit more in depth about specifically what you're doing, because that's like the overview of your whole group. You said you're looking at gas giants. Is that correct?
Yeah.
So, what kind of I don't know, like what kind of gas giants are you looking for? Like hot Jupiters, or like things that are slightly farther out? How are you going about doing this? Somebody asked before. Lynn Jersey asked before, where do you get your data from? Like what observatory?
Oh yeah.
So you can talk a little bit specifically about like the data you've been working with as well.
Mm-hmm. Totally. So yeah, my team gets pretty much all of the majority of our data from the Keck Observatory, which is on the Big Island of Hawaii at the summit of Mauna Kea. So that is where there are a number of telescopes up there, but there are two that are called the Keck 1 and Keck 2 10-meter telescopes. So these are some of the biggest telescopes in the world, and they're kind of sitting up on top of this mountain. And they're basically, I guess as the name would imply, they're like twin telescopes. So there's 1 and 2, and they're separated, I forget by how much, probably like 100 meters or something. And so all kinds of great observations can be made from that location, because first of all, there's very little light pollution, because, there are towns down on the rest of the big island, but it's not like huge cities. And then other than that, you're just surrounded by ocean. And then on top of that, you're also above a lot of the atmosphere that would otherwise kind of muddy the light that's coming in. So all of that, remember that we're looking for these signals of the star moving at sometimes very low velocity. Like the Earth is an extreme 10 centimeters per second, but even like a meter per second is not that fast. Like that. So looking for changes like that can get really screwed up if you've got like clouds rolling in front of you and like really high wind or just a lot of air in general. What you want is to be really close to space, ideally, because light can travel through space pretty much unimpeded. And so that's why you'll see most observatories are like on the top of a mountain or as high above the atmosphere as you can get. And then the last thing is that being on an island in particular, the air that's around the ocean is a lot less turbulent than the surrounding air that runs over land, because it tends to not develop these like turbulent flows that would otherwise screw with your observation. So that's why you don't see or one of the reasons, I guess, why you wouldn't see observatories like in the Rocky Mountains, for example. Probably there are other logistical concerns, but that's an easy reason why not. So most of it comes from the Keck Observatory, a bit from other smaller observatories, but that's our big workhorse because it's so powerful and gets us great precision. I have a good plot actually that I'd like to that I can bring up to answer the other question. So let me see if I can find this one. Yeah, okay, cool.
Have you ever operated the telescope from the remote room?
Oh, I wish. That would have been really cool. No, in general, what we do is we get to observe remotely. So you log onto a computer and we'd actually be set up on a Zoom call just like this, and you would be, sitting there at the telescope control room. And then so they have, you have your astronomer who wants to do the science, but then there's also the actual telescope operator who is charged with literally operating the telescope and making sure nothing goes wrong. So they're kind of, they're the professional telescope operator. You wouldn't, I guess, want an astronomer there who's potentially going, hopefully not, but is potentially going to prioritize their science over the safety of the telescope.
Yeah.
Which sounds very sinister. But I mean, it's not like someone would be out there like hacking at it. But things like, ooh, we can get one more observation before the sun comes up. And it's like, no, you might damage something. Or, oh, it's starting to rain, but we've almost finished this exposure.
It's like, no, we got to close it. Sorry.
Exactly. Exactly. So yeah, they're very careful and very serious about maintaining it. Okay, cool. So I found this that I think does a pretty good job of explaining where this one. Okay. Hopefully you guys can see that. Okay, so sorry, I kind of have some haphazard PowerPoints that I have put together for various talks. But I think this one answers the question that Vicky had pretty well. So why are we looking for long period, or well, actually, I kind of betrayed my answer a little bit, but why are we looking for giant planets at all, and what kind of giant planets are we looking for? So the short answer is we're looking for ones that are similar to Jupiter in the sense that they are, giant gas giant planets, but that are on long orbits. So hot Jupiters are a separate class that are very interesting, but are kind of divorced from the scientific goals that I'm actually pursuing here. So to give a little bit of background, and this will be kind of a long-winded answer, but I think it's worth it in the end.
Yeah.
The idea is, you guys have probably heard a bit about the transit technique, where you're tracking the periodic dimming of a star when an exoplanet passes in front, and so you can tell what the period and what the size of the planet are. And so the Kepler mission found lots of close-in small planets using the transit technique. And so this is a plot. You've got the semi-major axis, meaning the separation of the planet from its host star. And then you've got the planet mass on the y-axis. So, there are lots of close-in planets that have been found. You can see that 10 to the 0 is 1 AU, so the Earth would be at this separation. And then the number of masses would also be 10 to the 0 because it's 1 Earth mass. So the Earth would be sitting right here on this plot. Mm-hmm. And as you can see, the majority of these planets are a bit bigger than Earth and a lot closer in. So this is like 1/10 of an AU right here. So like 10 times closer in to their star than the Earth is to the sun. That's where you find a huge grouping of these planets.
Gotcha.
Yeah, and then the red ones are the ones discovered by the transit technique, and then there are some discovered by the RV technique as well. They're in blue. You can see that there are a lot fewer of them because they're harder to detect using the RV technique because they're so small. Okay, cool. So Kepler found a bunch of planets that look like this. They're very interesting because there are so many of them and because we don't really see any in the solar system. So the closest in planet in the solar system is Mercury, and it has a period of like 88 days. And like we saw, these are planets that would have orbits or orbital periods significantly smaller than that and be much larger than Mercury. So it's a weird class of planet, closer in than anything we know of and bigger than the Earth. Mm-hmm. So we're interested in that. Like, what's the deal? Why doesn't the solar system have this kind of planet?
Yeah.
Okay, cool. And so then separately, there's this new population. I mean, it's not new, but this one that I'm adding in, the distant giants. So these are ones, these are the ones that we're looking for. You can see that they're mostly discovered by the radial velocity technique, and they are kind of very massive and also a lot farther away. So I guess for some context, it would have been great if I had actually put these planets on here. But Jupiter is at about 5 AU, so you can count. So 10 to the 0 is 1 AU, 2, 3, 4, 5. So Jupiter would be at this separation. Mm-hmm. And then it's like 300 Earth masses. So 10 to the 2 is 100, 200, 300. So Jupiter would be like here somewhere. Okay. So even still, these are not exactly Jupiter analogs. You can see the majority of them are closer in than Jupiter and then more massive than Jupiter. But broadly speaking, we're talking about Jupiter analogs here. And yeah, we don't really know what the connection is between these two different types of planet. And I'll get to why that is in a minute. I'll just finish off the plot here, though. This is the population that Vicky was talking about, so hot Jupiters. Lots of these have been found as well. They're relatively rare, actually. Only about like 1% of stars have them, but we still found a lot because they're easy to find. Mm-hmm. It would kind of be like if you were standing in a crowd and there are like of 10,000 people, but there are like 5 people who are all 6'8". You'd be like, look, I found 5 people who are 6'8". There must be so many of it. It's like, no, they're really easy to find, but there aren't that many of them.
Yeah, definitely a confirmation bias kind of thing.
Yeah. And so, okay, so yes, but the important ones to look at are these two for my research. Mm-hmm. And you can see that, so distant giants have mostly been found using the RV technique, close in small planets mostly using the transit technique. And the reason for that, getting a little bit maybe technical here, but this is a plot showing the typical distance of a target detected either by RVs or by transits. And what you're basically supposed to get from this is that the typical transit target, the typical target that has been discovered by planet that has been discovered by the transit technique is at like 1,000 parsecs away. So very far away from the sun, very a distant system. On the other hand, the radial velocity technique, for the most part, we've targeted stars that are nearby to the solar system or to the Earth and are fairly bright, because this makes it a lot easier to overcome those precision errors that I was talking about before. So for the RVs, you want to look at stuff that's nearby, and it makes it easier to find planets. So the typical RV target is at like 50 parsecs away. Mm-hmm. So the distances aren't so important, but what you're really supposed to get is that they're two completely separate populations of stars, or almost completely separate. There's very little overlap between them. And so we've looked at some stars, the orange ones, and there are lots of close-in small planets. Then we've looked at a different set of stars, and there are lots, not as many, but there are some distant giant planets. But we haven't looked at very many stars to look for both types of planets. And so that means that if you look at a given star, you're like, well, I know there's a close-in small planet, but is it likely for there to be a distant giant planet, or is it less likely? Like, do they help each other form? Do they hurt each other's formation? We don't really know.
Gotcha.
And so that is the basis of the study that I'm doing. Um, the idea is you start with a system, or I'm sorry, you start with a set of stars that have known transiting planets. So we're like, all right, we already know it. We've looked at them with the transit technique. They've got a close-in small planet. Then we're going to follow them up with radial velocity observations to search for a distant giant. So the actual search that we're performing is for the big outer planet, but the close inner planet is really just as important. It's just that we kind of started with a set of systems that have known close-in small planets. And so that's kind of already a done deal. And so ultimately, we're hoping we can answer this question: how likely is it for these two planet types to form together?
Yeah.
And, do they help each other form, or do they hurt each other's formation? And that'll help us to really get the sense of how both of them form from the beginning.
And Slyquel's had another question related to this relationship. So they said, is one possible connection between these inner rocky planets a gravitational influence from the large planets that keeps the smaller ones from falling in? I'm assuming falling into their star. But I'm assuming these are the kind of relationship between these two types of planets that you're looking at. Is there some sort of influence that one would have on the other that would lead to them both forming?
Yeah, absolutely. So broadly speaking, that's definitely what we mean when we're talking about the influence. So could a large planet have a gravitational, exert some gravitational force on the inner planet and cause it to change its orbit in some way? Or could a large planet, before the inner planet has even formed, could it change the surroundings of the local gas and dust that's kind of hanging out around the star? Could it influence it to help it coalesce and create an inner small planet? Or maybe it could disperse the gas and cause it so that no planet can form. So those are generally the types of interactions that we're talking about. And then specifically, that's actually a really interesting question. So the question was, is it possible that a large outer planet could help a little inner planet survive by kind of holding on to it so that it doesn't fall in to its host star?
Yeah.
And one of the prominent theories actually kind of predicts the opposite of that, interestingly enough. So it does kind of make sense to think there's this big gravitational body, this outer planet, and it's going to hold on to this inner planet and make sure that it doesn't fall in. But over long periods, actually, the planets don't spend most of their time lined up. So this inner planet is going to complete a lot more orbits and kind of move around like this. And so there are going to be times when the outer planet and the inner planet are on opposite sides of the star from each other. So if the inner planet was going to just fall in due to loss of energy or something, it probably would, whether the outer planet is there or not. But what I mean by the opposite is that there's a theory that predicts that these two planet types should be anti-correlated, meaning you should see them together even less, let me be precise, I guess, that they would actually hurt each other's formation, right? So you would be less likely to see them together than you would be to just see them separately in different systems. And the reason is that the dynamical interaction between them, it's possible that the outer planet can periodically migrate inward toward the star for some complicated reasons that I won't get into, but it can sometimes migrate inward and essentially end up pushing the small planet into the star, which is not what you would think. And it's not you'd be like, well, gravity is not supposed to generally like pull objects toward each other, not end up pushing. And so it's not some weird like gravity reversal thing, but it is an interaction that these two objects can have with each other, where because of the inner one's migration, the small one ends up migrating as well and ends up just kind of falling into and melding into the star. And so in that picture, you would expect to see them in the same system very seldom, right? Because anytime there would be two of them, the large planet at some point would migrate inward and push the small planet in as well. So that's just a model of planetary evolution. It's not, well established. And that's one of the reasons that we're conducting this survey, because theoretical models don't agree. There are some that say that they shouldn't form together, and there are others that say that they should. Mm-hmm. And so that's why this survey that I'm conducting, it's called the Distant Giants Survey. It's supposed to be like really hitting the nail on the head with that one. It's supposed to answer that question, do they help or hinder each other?
Yeah.
That's a great question, though.
Yeah. I imagine the research too, like, it's really interesting to look at these exoplanet systems and compare it. And it's obviously not like a perfect analog to our solar system, but we do have the terrestrial planets that are closer to the sun and the larger gas giants that are farther away. And, seeing these other systems and seeing how they possibly could have formed, it's really interesting to relate to our solar system as well. So
yeah, that's true. That's one of the things that I thought was really cool about this project. So it's not like you said, it's not a perfect analogy because the inner small planets we're looking at are so close in that we haven't even seen them. But at the same time, we're kind of looking for like a solar system like system that has something close in and small and something larger and farther out. So yeah, in a way, the results of the survey could kind of tell us something about the origins of the solar system, which is, that's the goal in some sense, right?
Definitely. And so this is a little bit, I believe it's a little bit outside of the range of like what your research is, but I thought it was also interesting. Cycles before had asked a question about the difficulties needed to be overcome in order to detect exomoons, which is a whole other thing. But I imagine, with radial velocity methods, like there is, and please correct me if I'm wrong, but like the idea of like the larger body, the smaller body orbiting, there is probably some sort of radial velocity like going on there, like the same sort of shifting, but probably extremely hard to detect if
yeah. So that's a great question, and I won't claim to have specific expertise in the detection of exomoons, because I definitely don't. The intuition there, sorry, that the moon would also have an influence on the radial velocity of the star is definitely correct. As for whether, it's hard for me to say that the moon. There are some moons that are like quite large, and so they could have potentially a notable effect.
Oh, I was talking about like on if you could direct image an exoplanet, it would probably have an influence on the planet. In the same way that the larger system influences it, right?
Right. Okay. Yes. So,
yeah, because that would be really small if it was on the star.
My thought too. Yeah. So most moons would have pretty small effect on their host star. As far as on their planet, then yeah, absolutely, and probably a pretty significant one. To my knowledge, there is not much. I have not heard of radial velocity studies specifically of planets. It's really difficult in general to do anything with directly imaging a planet because they're so faint by comparison to their star. So there is an entire branch of exoplanet detection devoted to imaging planets. From my understanding, and Aidan would know a lot more about this, but it's kind of just enough of a win to be able to image the planet at all, let alone to be able to image it over long periods with high enough precision to do radial velocity analysis.
Yeah. Or to even really see if it has any moons.
Yeah, exactly. Yeah. But not, I don't want to also just throw out the whole idea, because think there are other methods by like that are more popular for looking at exomoons. I believe the transit method is one of them, where you can look for little like asymmetries in a transit, what's called the light curve. So the light curve just describes the brightness of the star over time. So it's kind of steady, steady, and then as the planet comes in front of the star, it drops, and then it's steady as the planet is in front of the star, and then it rises up again once the planet leaves. So it kind of looks like a big U. And so sometimes there are little asymmetries in that light curve because as the moon comes around, there's kind of an extra thing that is now in front of the star.
Yeah.
And yeah, I would definitely have to brush up on that because it's not specifically what I work on. But yeah, suffice it to say that there are avenues that people pursue to look for exomoons. Not radial velocity, as far as I know,
Yeah.
although definitely cool.
Yeah. Exomoons are like a whole interesting thing because there's the whole idea of like, oh, well, we're looking at moons in our own solar system now for like habitability and stuff, and it's like maybe that would be, but like imaging exoplanet, like finding exoplanets is already so hard. I imagine it'll be a while till we have the technology to really look at exomoons, but it's cool.
Yeah, no, it's awesome.
Yeah. Another question from chat that I also thought was very interesting. So going back to the whole idea of like a gas giant and a close-in terrestrial planet, you know, forming together or not. Do you think it would be possible for a system with these small rocky planets like Earth and closer to not have something a gas giant farther out like Jupiter and still be viable life targets? I think they're getting at the point of like some people theorize that the reason life was able to form on Earth is because Jupiter catches a lot of stuff that would have impacted Earth and ruined everything. So do you think that's like I don't know how much you guys are looking at habitability kind of stuff, but
Yeah, no, I mean it's a good question. As far as yeah, so well, let me back up. Sorry, I don't
no, you're
catch them.
good.
I don't want to say too much. Um, so my group does not really focus on habitability, or at least the specific work that I'm doing. That doesn't mean that we're not thinking about it at all. As far as the idea of Jupiter kind of being necessary for the formation of the Earth, it's interesting. There's a little bit of nuance to that theory because, of course, there's kind of the original theory of like of Jupiter as a shield to asteroids and so on that would have impacted Earth. Um, I looked a while ago. I'm not sure if this is the most current theory on it, but maybe like a year ago, I was kind of checking out that line of thinking. There are some counter theories to that one, which instead suggest that Jupiter is still important to the formation of the Earth, but not for blocking the impact of other objects, but instead of actually delivering
Oh,
impactors to the Earth. So, like, the idea is that Jupiter sits beyond what's called the ice line, generally where an object would be able to support liquid water interior to that line because it's close enough to the sun that it would, that the water would be melted. And then outside of that line, you would see mostly frozen water.
mm-hmm.
And so there's this hypothesis that in order to form the amount of surface liquid water that the Earth has, it would have needed to get icy, like asteroids and icy little objects, kind of migrating inward from beyond the ice line to then hit the Earth, melt, and form the water that we see today. And the idea is that those dynamical interactions that I was talking about earlier, I know that's kind of like a term that's pretty vague, but basically, Jupiter's gravitational interactions with the things around it
Yeah.
could have caused those things to migrate inward and collide with the Earth and subsequently form the oceans, for example. So yeah, there are various theories about whether or that explain how Jupiter could have been important to the formation of the Earth. Um, yeah, it's an interesting idea. I'm not sure that any of those are like 100% accepted as
Yeah.
being like, yes, if Jupiter hadn't been here, then we wouldn't have water on Earth, or that Earth would be, wouldn't be here. um, yeah, it's hard for me to say exactly like the level of precision with which people are claiming that.
Yeah, there's
Um,
a lot of lots of theories and stuff as far as how life got. We have no idea how life got here. Still, there's so many different theories, but like
right.
it is a really interesting line of thinking, and it's another thing that like um, contributes to why this relationship between these different types of planets is so interesting. I think.
Yeah, it absolutely is.
Yeah.
Yeah. And so, right. So I wouldn't want to disparage that. It's I mean, I think possible that without a Jupiter-like planet, that we could still have formed, a habitable planet. I can't really say either or, but what I will say is that there are, again, I keep referencing these theories because, like I said, prior to this survey, that's kind of all we had. But the close in small planets that we're looking at, we don't really, I mean, we're not claiming that any of them are habitable. What we're saying is that they're just small and they're close into their star, and we are quite sure, I mean, we are sure that those can form in the absence of an outer giant.
Yeah.
um, and yeah, the reason, well, first of all, the reason for that is observationally, we do observe some systems where we see the inner planet transiting, but there's no evidence for an outer giant.
Yeah.
And so whether those things are habitable, completely different story, and probably they're not because they're so close into their star that, I mean, it would be
It
hard
would.
to support any kind of atmosphere.
Yeah. I mean, Mercury is a good example of how being close to a star, you're not very is very very low chance of being habitable, and
Yeah,
they're even closer than Mercury, so I don't think it's gonna go well.
that's
But
right.
yeah,
Yeah,
still, still very cool.
yeah, definitely.
Well, we are actually at the end of our hour. We usually stream for an hour. So I think we'll probably wrap it up here. But before you go, is there anything else that you wanted to talk about? Any other things you're interested in? Any stuff you do outside of research things that you want to let people know about? I guess I don't know.
Wow. Let's see. I probably should do more outreach. Damn.
Oh no, it's okay.
I don't-
This is outreach. This
I
is
know this is what I'll
you can
plug
write this
next
down.
time.
Yeah.
Yeah, cool. Let's see. Probably not like any events or anything. I guess I've got a little bit more of a description of of the work that I've just been talking about here on my website that I've been putting together. Still under construction, but it's just my name, Judah Van Zandt, VanZandt, and then it's got like a weird domain name. It's like .webflow.io. So you can tell that I've really been working on it myself. JudahVanZandt.webflow.io, and
Let me find it. Oh, there you are.
yeah, so it's a little bit,
Put it in the
the
chat.
research is not completely fleshed out, partially because I haven't had tons of time to do it, and also partially because the really exciting stuff that I wanted to put up there I'm kind of getting close to publishing it, and I don't want,
You can't put
you know,
that stuff up before you publish, yeah.
yeah, I mean, I don't think anyone's going to be like looking at my website and like scoop it, but
Yeah.
yeah, my girlfriend was pointing out, she's like, should you really be putting that up there if you haven't like published it yet? And I was like, that's a good point.
Yeah.
So yeah, intro to the distant giant survey. I think you can read more about that. And then the real, like, some of the details of the challenges and stuff that we've had to overcome along the way are hopefully forthcoming. Um, yeah, and then I don't know if people are interested in looking at papers that come out, but hopefully in the next month or so, maybe 2 months, I'll be putting out a paper on like the first results of the distant giant survey.
Oh, that's
So
exciting.
so it's ongoing, but we've discovered a couple of planets so far, and so I'm going to be writing those up and saying like, where are they? What does this mean for the results of the survey eventually? So it's kind of like a nice little update. So
Nice.
yeah, if you happen to be like cruising on the archive where these papers get posted, I don't know if you
The
would be.
Google Scholar or whatever it's called.
Right. Yeah,
Yeah.
so you can check those out.
Yeah.
Maybe see my name.
Yeah, we'll share it. Let me know when it goes up, and I'll let people know on Teach Astronomy. So,
Cool. Will do.
well, thank you so much for being here. Thank you for chatting with
Yeah.
us.
Thanks for having me.
Everybody in the chat says thank you. Lynn Jersey said thank you for taking the time to talk about your research. Very interesting. Yeah, and I I think that's about it. So I'm just gonna do a couple housekeeping things real quick before I let you go, Judah. But
Oh,
as far as the rest of the week goes, guys, on Friday I actually have to cancel stream because I'm going to be working my other job. But next week I will be back with our regular Monday. We're not going to be playing Kerbal Space Program. Normally on Mondays I play Kerbal Space Program here with a friend, but the friend will not be able to make it, so we're starting a new game. I will let you guys know what that game's going to be. And then on Wednesday, we'll be back with some astronomy news. And Friday next week, we're starting Dungeons and Dragons in Space again. So if anybody's interested in that, come hang out. Judah, if you ever want to play Dungeons and Dragons in Space, let me know.
in space?
Yeah.
That's pretty cool.
We have a friend that also streams on the channel. Oh, thank you, Grant. Okay, someone in chat reminded me. And next Tuesday, I'm going to be on Grandpa 9000's channel, who is in the chat right now. If anybody wants to go follow him, do that, please. We're going to be playing Phasmophobia at like 6 o'clock in Pacific Standard Time at night. And I'm going to get very spooked. It's going to be fun. So you guys should come and hang out. But I think that's about it. But yeah, we play Dungeons and Dragons in Space. Grant, that same Grant, hosts, does the game mastering, and has invented a whole world for us to explore. It's very fun. We explore exoplanets. So yeah. But I think that's about it. So thank you again, Judah. Thank you everyone for watching, and we will see you next time.
Awesome. Thanks. Bye, everybody.